user interface. And this basically extracts a snapshot of your model at any time. So it doesn't have to be at the end of the simulation. Anytime you stop or pause the simulation, okay, it takes a snapshot of the fluxes, grams per day, typically, at every terminal of your process model, every tank, every sensor, every block in your layout. And you can save this as a CSV and then open it in Excel, like I've done here, to show you a typical output. You have a simulation time here indicated, so this is a snapshot at day 30. It also represents different, if you have different state vectors, different main process categories in your model. This is a same one for the waterline, for instance. And in this layout, there was an anaerobic digester, so ADM1 state component. So you have both, and you have the state components here, and what we've added to work with, in combination with the mass balance tool, some more conventional lumped aggregated components, BOD, COD, TN, TP, TSS. We're going to add VSS, for instance, soon, to allow for an easier mass balance verification. I've highlighted here an example. This is around the secondary clarifier, and based on these figures, you can work out, in this case, COD and TSS removal. What I personally have found this tool particularly useful at, and I'm almost sure it will be the same for you, is in identifying inconsistencies in your process flow, and even mistakes. In one project, I realized that I set wrongly a solid removal in one of the clarifiers, for instance. So I was losing solids where I was not supposed to lose solids. And this is a very easy verification tool to check this. I mentioned that we are maintaining, improving, in particular the latest models that we introduced with recent versions, and this is the case for N2O, the N2O model. In 2025, we've revised the default set of parameters, and now so that different ASM2 flavors of that you find in West, what is called ASM2D mod, ISS, now NDHA, are all consistent in the common elements. For instance, nitrate, and it's like a baseline, so all will predict the same level of nitrification, denitrification, and obviously different versions of different variations of the model will add some complexity into the process, like NDHA. There's a more reliable description of the stripping mechanism, and particular Barbara is has been working on this. And like I mentioned earlier, there are now two options to incorporate N2O emissions in the cost balance. One, the conventional that we've had in West for a few releases now, an empirical correlation through an emission factor to the influent nitrogen load. And now with this N2O emission model, production model, based on the actual N2O production simulated through the model. We've also included N2O emissions due to a residual N in the effluent, of course, and these are some examples of output. we've also upgraded, improved the micropollutant, the ASN2D mod MP for micropollutants. It's mentioned here IUVWS library because this is incorporated in this library called IUWS4. We've now selected one micropollutant of reference, carbamazepine. So all the kinetic parameters in the different sections of the models were treatment and in conventional treatments and quaternary treatments are represent carbamazepine. So if you need to model a different micropollutant, all you need to do is change this parameter set to represent another micropollutant. But we've also going to work out a solution to potentially download a set of parameters to represent multiple micropollutants that can be then plugged in into the model in a easier way. We've also updated the ozonation model to be able to account for the effect of solids and pH. And we maintain, of course, the cost calculator, which is a key element, of course, in process modeling to accommodate for all these changes, and in this case, for energy consumption and chemical use in chemical dosing. So depending on the framework that you use, N2O model, the micropollutant model, you will be able to calculate the costs of the relevant processes in your model through the cost calculator. In the last version, a lot of work has been gone into the biofilm model, not really in terms of the process description, but in terms of performance of the model and the simulation. One issue has always been simulation speed, and particular initialization. Due to instability, numerical instability at the beginning of the simulation to get the biofilm layers started correctly. And this was due to a very hidden issue in relation to variations of the concentration. The derivatives of the concentrations were highly were changing very fast. So again, what Chris worked out is a very efficient mechanism. We've added 3 parameters to the model that you see here. If you have used biofilm model in the past or plan to use it in the future, these are 3 key parameters, and in particular, this initialized biofilm masses, a flag that you can set to true, to 1, if you want this special initialization routine to be executed when you launch the simulation, and this will allow for a smooth start up of your simulation. And here is an example of this is 1 year of simulation, and I think it took a few minutes, I think to run. With previous versions, it could take a long time, or even not start properly unless you manually inputted the right initial conditions, which is obviously not always possible. I also mentioned that we worked on the documentation, so this is has been lagging behind for some time. Now we are busy maintaining it constantly. In West, you find in the usual place a link to the various sources of documentation. We particularly worked on this models guide. It now looks like this, and it is obviously linked to the current Modelica library. It's an example of what you see for the biofilm. And we've developed, rolled out this self-paced training. I think we estimated the plan looks like this. There are 7 modules that cover the very basic elements of West, how to set up a project, how to calculate statistics, KPIs, but how to add some custom calculation, how to control aeration, and so on. 7 modules, and this would we estimate take about, I think, 7 hours or so, 7-8 hours, and that can be spent at your own pace if you should want to enroll. And the course has an accompanying self-paced training guide. Now, what are the plans for the future? I think I have so much time left, but for the immediate next version, this is what we are working on: complete redesign of the Influent Wizard that will incorporate the fractionation, probabilistic fractionator that Chris is going to talk about next. Then we will improve some functionality of the mass balance tool. For instance, better formatted output and not just CSV. We are working on extending the Python interface. For instance, the ability to use West in Python and execute, for instance, models through Python, but also write Python code inside West, and for instance, associated to a controller icon. So define the control algorithm in Python directly in West. And we are looking at improving some solvers, adding new solvers and improve performance in some of the solvers in some specific situations. And then we are looking at the full adoption of Modelica in the direction of running FMUs, functional mockup units, that would potentially make simulation, compilation and simulation faster. So these are the plans. And I forgot about this one. Yes, we're also working on developing models more directed towards industrial wastewater and potentially also drinking water treatment. In the 5 minutes, I think, that I have left, I'm not sure I can do it, but I want to, as I said, it's slightly, not strictly CO2 footprint related or process optimization related, but I wanted to show a very recent application of the models that we developed, and this is for in the scope of a master thesis that we supported. And the work was around BPA. It's an organic compound with important environmental effects, both on human health and environment due to biomagnification. And that has a significant production already, and even more significant projected production in the next couple of years. The objective of this work was to suggest some practical solutions as practical as possible, quantitative as possible, to upgrade a Danish, because this was the test case, treatment plant to prepare for the recently approved new regulation in Europe in relation to micropollutants, and this is a requirement that for this type of micropollutants that has been adopted by the Danish EPA. The plant is a large plant. You see here some key figures and characteristics with the mechanical pretreatment, primary treatment, secondary treatment, and then discharge to the sea between Denmark and Sweden. So the idea was not to model the conventional process that had been done in the past and a lot more sophisticated than the very simplified version of the model that we've adopted, in particular because it has multiple trains, parallel trains, and has a very advanced aeration control and regulation mechanism. We simplified the conventional treatment to this very basic process layout. And the work on this thesis focused on what could be after the secondary treatment, the usual biological treatment. And we looked at activated carbon and ozonation and the combination of the two. So these were the scenario that this student assessed. Baseline, that's the current situation. What is the predicted concentration of PPA in the effluent? And then possible solutions for the future: addition of activated carbon, ozonation, or the combination of the two. So at this, with this process setup, the utility would have around 70 nanograms per liter in the effluent of PPA. Here in red is the target, so significantly above the quality required for the effluent. Now, applied the granular activated carbon model in West on the secondary effluent, and we verified that was obviously effective up to a certain point. And here you see the breakthrough curve for the carbon with an expected estimated limit of 86 days, this equivalent to 3,600 bed volumes, and with an estimated consumption of carbon of 0.12 kilos per cubic meter of water treated. You will see these numbers will improve, obviously, in the combined configuration. Then, for ozone treatment option, we've evaluated, we've tried to evaluate the uncertainty of this key parameter, and we isolated two extreme cases, both capable of meeting the requirements. You see one with an average effluent quality of significantly lower than the limit, 1, and the other one closer to the limit of 8, obviously with different doses of ozone. The combined scenario resulted in overall better performance, of course, with less, half of the consumption of carbon, and also almost double. I think it was 80, this 172 days until the carbon column needed to be regenerated. And this allowed for some conclusion, also practical suggestions and indication to the utility in terms of quantities of carbon used, doses of ozone necessary, and the pros and cons of one or the other process configurations. And with this, I'm almost perfectly on time. I hope, you have some questions. Yeah.
Well done.
Thank you,
Enrico. That was pretty impressive in terms of your timing. Yeah, the floor is open to questions. We have 10 minutes, so if you'd like to pose a question to Enrico, please do so now.
Anything in the chat? No.
There's nothing in the chat directly for you.
Okay.
Enrico, sorry. One of the aspects that sort of previously I've seen with West users, and I just want to have a look at it, is it's a very flexible model, which has got a lot of sort of ability to customize and stuff like that, which is fantastic. But with that kind of comes the difficulty related to the configurations, because it's not there's not really sort of easily standard processes and stuff like that. And you sort of touched on it a little bit in your discussion, but is there a sort of method where you can look at sort of templates and stuff like that that is handed to the users so they can get started a little bit easier on some of the processes? Is it something that you're having a look at?
Yes, and no, but it's a good idea, a good suggestion. So yes, because they are already in the with the installer. When you install West, it comes with a number of samples and templates. We should, that's a good suggestion, of course, prepare a couple of more templates, especially in relation to these new models. But what is also interesting, I think, from a user perspective, is that the end user can also create their own custom templates. We can do some for them upon request, I think, but also as a user, one can save a project and can prepare a template that can then be reused multiple times. So it's, yes, I think it's a very interesting feature that we should develop more. Yeah.
Excellent, thanks. Are there any questions from the floor? Please raise your hand if you've got something.
You see West being used for operation, for example, where you have a plugin or API that integrates online sensor data with for simultaneous analysis. Yes, and if I interpret your question correctly, that's what we have already started doing. At DHI, we have this solution called TwinPlant. Sorry, because that comes up and hides the messages. This solution called TwinPlant that aims exactly at that. So we have a calibrated conventional waste model of a plant that is connected in real time through the SCADA to the sensor on site. And the system at TwinPlant acquires sensor data regularly, executes simulation automatically, and there's also, of course, the option for the user to launch simulations whenever it is desired. And then you can monitor the operation of the plant in the standard mode where you compare prediction of the model to the actual operation of the plant through the sensor. But then you can also use this system for scenario analysis and for prediction. Yeah, then there you go. So Fabio linked to implant in the chat, so you can have a look. But yes, that's what we have been doing for the past couple of years.
Yes, excellent. I think I should also mention that DHI has a number of these types of implementations where you run real-time information with applications. It's not just with West. And they are very useful, these twin plant operations, because when you get deviations from what you anticipate or expect, it usually indicates that there's either some sort of physical problem on the ground, or alternatively, it allows you to improve your modeling applications quite effectively. So yeah, it's quite useful. Enrico, just maybe to wrap up and finish off, I know that we focus quite a lot on wastewater treatment work solutions and stuff like that. Sorry, you've got a question there. Do you think twin plant then takes away the need for sensors? I'll let you answer that.
Soft sensor. Well, that's what we are. One of the goals of this online solutions is indeed that of mimicking a potentially real sensor through the model, and the model will provide a virtual sensor where there is no sensor in reality, or there cannot be a sensor. Yes. Applied in sewage plant to monitor metal fluxes. It can. I don't think we have any model off the shelf that models metals, but this, as Jason mentioned earlier, the model framework in West is entirely open, so there's no restriction to adding new components, as long as we have mechanism. We know the mechanism of transport and the solution and things like that can be modeled in West. Yes.
Oh, that's great. Yeah, I was just going to say that from my knowledge, your applications are not just in the wastewater treatment work sort of scenarios. You have used it for other applications. I think you even used it at one stage at Sasol for some of the efficient trucks process monitoring. So it is extremely flexible, the modeling application related to these things, and it's quite exciting from that perspective. Anyway, I'm going to okay, let's just see. I'm going to let, with regard to soft sensors, based on some assumptions, a perfect distribution model allows essentially to take measurements anywhere in the plant. Okay. All right. Thanks, Christopher. Yeah. All right. I'm going to wrap up, and let's move on to the next presentation. Thank you very much, Enrico. I'm going to move on to Chris Burkhardt, who's actually well, I don't know whether you're still based in South Africa, Chris, but was definitely in South Africa at down in Durban, and has been intimately involved with the applications and running of West. There's two development centers in South Africa, one at the University of Cape Town and one at University of Durban. So it's good to have some local experts here, which is fantastic. And can we hand over to you, Chris, and let you take over for your presentation? Thanks very much, Enrico.
Okay, well, this is me. Yes, indeed, I am in Durban. I was at the University of KwaZulu-Natal for 35 years or something, 40 years maybe, starting as a student. I'm now retired, and in my retirement was fortunate enough to be engaged by DHI to help to join the development team. Okay, what I'm going to, so I wasn't expecting Enrico to introduce my talk, but it is in connection with the work that we did. So we initially developed the probabilistic fractionator for use in Durban. So let me open up, share my screen. Here we go. Which one? There we go. That one. Go into presentation mode. Yeah, go. Why is it not going?
Because if you hit the bottom sort of middle there with that slide sort of shows, I think.
There you go.
Okay, well done. Yeah.
So the probabilistic fractionator, influent fractionation for Africa. I'll explain why I use that description. So when we want to set up a model for a real wastewater treatment plant, there's two major things that we need to know. The first, of course, is the equipment configuration. What equipment do we have and how's it connected? And the other thing that is critical is the characterization of the influent. And that's because everything that the plant does is dictated by the influent. The influent, even the microorganisms that do the treatment are derived from the influent, and they adapt to its characteristics. So if you have the wrong characterization of the influent, you can't really expect to get good results. Now, the problem is that models require the fractionation of the influent. It's got to, the measurements that we take have got to be assigned to a whole series of different components. There's soluble components, there's particulate components, there's biodegradable and unbiodegradable components, and so on. And the model needs these to determine the fate in the treatment process. Where do they go? Where do they end up? And so we show, the diagram shows a fractionation scheme for COD and for TSS at the bottom. And the same goes for nitrogen and phosphate and sulfur and whatever that you might be interested in. So the model can't work directly with the raw measurements. Now, the standard West approach has been to use an algebraic fractionator, where the measurements in blue are converted to the components by a series of algebraic equations, which you can see there. And that works quite well if all the measurements are accurate and consistent with each other. Unfortunately, when you're dealing with what I would say African data, that is often not the case. And then you get inconsistencies, and some of them are quite serious. You get negative concentrations of components which are physically unrealistic, so sends the model into limbo, and sometimes causes numerical problems, and so we were, when we tried to use normal plant data, we would find that the simulation would often just crash. Okay, so and there's a number of problems with using the routine data. First of all, gaps. So this is a particular record from a particular plant in Durban. And what you see is that, yes, they measure the flow every day, but the COD only every so often, every 2 or 3 days. TSS the same, FSA the same, ortho P even less frequently, and TK and total phosphorus, they'd stopped measuring for some unknown reason, so no data at all. So the first problem is those gaps. West don't like gaps. So the idea was then to find a method that would use whatever information was available and come up with the most probable composition. So not connected to the measurements in a fixed scheme, but adjustable to take into account whatever information is available. So we have measurements. From those, we can calculate estimates by a simple proportional scheme, and then we fractionate those into model components. So that's the objective. And to try and use all the information that's available, which includes literature information, the measurements themselves, the knowledge of the plant, and lastly, the judgment of the modeler, which we'll see how that comes in. So the estimated measurements which are used are simple proportional relationships, and the default values we get from literature, they can be adjusted by the user to suit a particular plant. So basically, the IWA, biological wastewater treatment handbook, the chapter on wastewater characteristics, that's where the default values of the factors come from. So as I mentioned, the first thing that we have to do is get rid of the gaps, and we do that by interpolation. But what then happens is that you can get actual measurements at a particular time being combined with interpolated measurements. Now, an actual measurement is obviously more reliable than a measurement the day before or the day after, or maybe 2 days before. So the weighting, the priority that we give to interpolated measurements is less than the priority that we give to real measurements. And so the West cannot see into the future. So we have to do a bit of pre-processing of the data, which includes the interpolated values, which are colored, and the weightings, which are then calculated according to how far the measurement is, how far the interpolation is to the closest measurement. So is it shortly after a measurement, or is it shortly before a measurement? The time gap is used to calculate a lower weighting for an interpolated measurement. So this is what a record of routine measurements on a particular plant look like over a year. And as you see, lots of scatter, lots of variation. So how does the algorithm work? Well, for any particular, at a particular moment in time, if you have a composition calculated from previously, there's two things that we calculate. The regression has an objective function, and the idea is to, which is the objective function is the sum of squared errors between the measurements or the estimates and the simulated measurements, which are calculated from the composition. So if you have a particular composition at a particular time, there is an objective function which you can calculate, say, at a point like that. The best fit is at the bottom of the curve. Okay, so the next thing that you calculate is the derivative or the gradient of that objective function, which is the steepest slope towards the optimum. So we don't jump to the optimum point in one step. At a particular time, we move the composition down that gradient at a rate which is determined by the steepness of the slope divided by what I'll call a smoothing factor. I'll explain why in a moment. So if we have this is a comparison of the measurements against the simulated measurement calculated from the fitted composition using a low smoothing factor. So what is happening is that because the measurements are changing all the time, that optimum point is moving around, it's jiggling around all the time. And with a low smoothing factor, the optimum composition tracks the optimum point more closely, and it jiggles around with it. So you can see that it's really jumpy. It's affected by if you look at this point, it's really following what is probably a wrong measurement. and so on. So the user has the option to change the smoothing factor. And here, if I have a high smoothing factor, now it's clearly too average. It's responding only to very general changes. So, and then somewhere in between, you get something which looks as though it probably reflects the plant conditions properly. Now, I've just done this by eye, so this may not be the best, but I would hope that somebody associated with the plant would have a better feeling for how that should be set. So the point then is that we are. This gives the ability of the modeler, the user, to exercise his judgment in determining what are the what is the best representation of the influent. Now, I mentioned that the TKN and the total phosphorus were just not measured, and this is where the estimates come into their own. So this graph shows the estimates in the yellowy color, and the resulting fit of the composition to the estimated TKN. So and what we see, so essentially the estimates then represent the biological wastewater treatment factors, and it shows that at least they are consistent, that the compositions. So without actual measurements, we don't know if these are correct. That's the fact. But at least we can say that our factors and our components are consistent with each other. And indeed, for modeling purposes, now we have those second-class measurements to work with. Then Enrico did mention that the objective function gives us a facility to evaluate how well the fractionator is working. So the objective function represents the how can I put it? It represents the inconsistency between the degree of inconsistency between the various measurements and the estimates and everything that goes into the to the fractionation. So where you see a spike like that, it means that there's something particular that is not agreeing with the other bits of information that go into the determination. And the objective is the sum of contributions from all the various components, so including the estimates, including the measurements, including some other parameters like limits on the variable. So for instance, variables are not allowed to go negative, and an inconsistency might be that the objective is trying to make it go negative, and then that will result in a higher sum of square errors. Anyway, the point is that we can look at a particular peak and say, oh, what's going on here? And I think I chose this very high one over here to examine. So if we zoom in on it, there it is.
Chris, sorry to interrupt you. I'm going to give you an additional 5 minutes. You're already over time, but I'm going to let you continue.
I think this is the second last slide.
Okay, cool.
So what we see is that this error is dominated by one term, which happens to be the TSS. Okay, and if you go and look at that point again, there's that point, and you can see, yes, that was a real outlier. Now that's just one example of how you can examine the output to see what's going on. Right. So to summarize then, the fractionator provides a number of parameters for tuning to a particular plant. I haven't dealt with them all, but I've dealt with the smoothing factor, the estimation ratios. There's some, then I've mentioned upper and lower limits on fitted components, upper and lower ratios on matched measurements. So matched measurements mustn't be more than some ratio than the estimate. And to summarize then, characterizing the influence is one of the most important steps in modeling a plant, and it's worth some effort to get it right. And this fractionator provides a number of means to help with the task. And that's where I end. Thank you.
Super. Thank you very much, Chris, for that presentation. Do we have any questions from the floor?
Stop sharing.
So, Chris, I must confess, I got a little bit lost on one of the sections there. Oh, thank you. Okay, let's have a look and see what's in comments here. What is the main hindrance to better simulations modelings according to your vast experience, Chris? Secondly, when the influence is characterized, how does it fluctuate? Chris, yeah. Can you see the comments and see?
Yeah, yes, I'm just thinking about the answer. Thinking about my reply. So, you know, the first question, what is the greatest hindrance? It really depends on the plant and the data that's available. Certainly, so I was at a conference and at a particular presentation, they presented a modeling of a plant, and the one of the standout comments was that the preliminary measurement campaign to before they even started took several months and involved more than 2,000 individual chemical analyses. Now, one of the reasons for the probabilistic fractionator was that we're working in Durban, that kind of approach was just out of the question. So we had to make do with what we had, which was the routine data. And so this probabilistic fractionator was a response to one of the key hurdles to doing modeling in this environment where you just don't have the resources to follow the standard modeling good practice procedures. So that was the first question. The second question was the characterization of the influent varies as the measurements vary. So it's a new characterization for every new set of measurements. If you have very high resolution data, you will be able to characterize the influence perhaps throughout the variations during the day. With the sort of data that we were working with, where you have measurements only every 2 or 3 days, obviously the characterization moved much more slowly, and it meant that you have to look and see what kind of modeling can you do with that data. You can't do modeling which looks at the influence of diurnal variation on the plant, but you can look at things like what happens if your sludge pump breaks down, or what happens if you have to accept an extra load of effluent from a new housing project, and so on. So that those are the sort of questions that were often addressed or needed to be addressed in the African kind of context. So the characterization varies according to the resolution of the measurements. That's the short answer.
Thanks, Chris. Chris, yeah, my question was actually quite similar to that. Was one of the aspects that really sort of influences a lot of the sort of processing that I've seen in wastewater treatment plants in the Southern African context is the variations that we have in the influent water quality. What I've seen in places like Europe and those types of things, where they able to look at some of the more sort of let's call it sophisticated processes, like putting in sort of bio reactors and stuff like that, to biogas generators. Seems to be a more sort of consistent influence stream. And I just wonder what your sort of comment on that is, and whether this influence characterization actually helps with that.
Yes, I mean, the answer is more or less the same. Is that whatever so you could see, for instance, in that year's data, you could see the changes of summer versus winter rainy season versus dry season and so on. Those things you can see. You can't see what happens during the day or really during the week, because the data is not good enough. If you've got the data, you can see those variations.
Yeah, cool. All right, excellent. Thanks very much, Chris. I'm going to move on to Barbara now. Thanks for that presentation, which is excellent as usual. And thanks very much, Barbara. Can we hand over to you?
Hi, yes, I'm Barbara. I'm also from Durban originally, and worked at UKZN for a while, and we're working with eThekwini on wastewater modeling and trying to make it more accessible to South African municipalities. I would say though that the kind of data issues, I think they may be a bit more extreme in the South African context, but I'm sure our European counterparts will can attest that they have problems with data as well. It's not just us. Okay, so my presentation is somewhat of an extension of the previous one. And it's using routine data to estimate the biodegradable CO2 fraction in wastewater, using the KwaMashu treatment works in Durban as a case study. And there was a discussion in the chat about WIPs, and the KwaMashu model is essentially, I guess, a WIP. Our colleagues at eThekwini called them skeletal models. They partially calibrated models that you can use to make this decisions with, and that you can improve over time as more information becomes available. So the background to this study, it was part of a project to look at encouraging resource recovery and wastewater treatment plants, which was led by the Danish Technical University, and we were at the time working very closely with eThekwini, and it fits in with the goals of that partnership as well. The reason KwaMashu was chosen as a case study was because they were planning an upgrade, which would include at minimum the addition of phosphorus removal. They're also considering nutrient recovery, possibly water recovery, and thermal hydrolysis to enhance energy recovery.
Barbara, are you sharing at the moment? Or?
Oh, I'm so sorry. I thought
Okay.
I skipped
Sorry.
that stuff. I beg your pardon.
So
Got ahead of myself
there.
things. Oh yeah, no. I skipped a step. I'm so sorry. Okay, so let's go back to, there we go. Share screen. Okay. Now am I sharing?
Okay, thanks. Yeah, we can see.
There we go. So let's see, slideshow from beginning. All right. So there we go. And this is where I got to. Yep, the current configuration, and the future was hopefully phosphorus removal and possibly these other resource recovery options. So the first step in modeling an upgrade is to calibrate the base case model, the current configuration, with available plant data. And as Chris already mentioned, getting the influent fractionation is really important, especially in this case, because the configuration is going to change. The process and microbial population is going to change as well. So what you need is the correct influent characterization to try and predict how these changes are going to affect the plant performance. So the influence fractionation tool that you're just discussing is a tool for calibrating the influent, but it has a major limitation, is that it has no way of discerning the difference between the biodegradable and non-biodegradable fractions in the wastewater. So what it uses is these estimates based on ratios. So for example, the unbiodegradable oh, I did not mean to jump. Okay, never mind. So you have ratios from the literature usually to describe the relationship between the different fractions in the total measured COD. Okay, but the fractionator itself can't tell whether what's biodegradable and what's not biodegradable. So we've already sort of gone through the concept of fractionation. At minimum, we need to fractionate the wastewater into soluble biodegradable, insoluble biodegradable, biodegradable particulate, and unbiodegradable particulate. Most models have a component for either total suspended solids or inorganic suspended solids, and the volatile suspended solids will be the rest of the particulate fraction. Now, the sorry. So the fractionation of the wastewater is really important because it determines the fate of the different parts of the influent in the plant model. So for example, your soluble unbiodegradable COD passes through the plant unchanged, goes into the secondary effluent, and it limits the minimum COD you can achieve in the effluent. So that's an important fraction to know. The biodegradable soluble is rapidly consumed in the activated sludge plant, and it's important in nutrient removal. The biodegradable particulate is the part which degrades, resulting in the solids reduction that you see in the treatment plant. When it degrades, it also releases nutrients. And then the unbiodegradable particulate, that's both the organic and the inorganic part, just accumulates in the sludge. So it affects your mixed liquor suspended solids and also your overall sludge production. So it is possible to measure the biodegradable fractions of wastewater, and methods are listed in the chapter 3 in experimental methods in the IWWA handbook, but it requires specialized equipment. It's time consuming, it's expensive, it's difficult. Most municipalities don't have the equipment or the personnel to do it. Some plants use BOD as a surrogate for biodegradability, but those measurements also take a really long time. You actually need a model to relate them to the biodegradable fractions in the wastewater treatment plant. So, however, as we've been discussing, the fractionation of the wastewater predicts what happens to the different parts of the COD in the plant. So the question is, could we extend the methodology of the fractionator to include other types of measurements which reflect the fate of these components in the treatment plant in order to infer the wastewater fractionation? So this led to the development of the COD fractionation tool, which I'm going to describe. And it was developed in the context of the Kwamashu study as a result of having to deal with issues of missing data. So the one lot of missing data was biodegradability, and that's normal, but there were a number of other issues. As Chris mentioned, doing proper sampling campaigns for modeling usually is not an option for us. It particularly wasn't in this case. This was in 2020. There was COVID. There was load shedding. wasn't going to happen even if we'd had the budget to do it. And load shedding in particular had been a big problem, I'm sure for a lot of plants. But in Kwamashu, it had disrupted operations to the point that the 2020 data wasn't useful for modeling. So we were going to use data from 2018, where things had been less disrupted. But in the meantime, the storage system where the SCADA data was backed up had been damaged. And so that data wasn't available to us. So, for example, we had plenty of laboratory data for different streams, and we had the flow into the plant. But that was the only flow data we had. We didn't have the flow to the anaerobic digesters, so we couldn't calculate the hydraulic retention time. We did not have the waste sludge flow, so we couldn't calculate the sludge age. We didn't have the flow of the nutrient-rich supernatant liquor. We did refer to the design data to try and infer some of these missing measurements, but the other plant problem Kwamashu is having is problem with their solid removal contract. So they were running it from longer sludge ages and design. So even the design data wasn't necessarily reflective of what's going on. So our goals in developing the COD fractionation tool were twofold: was to generate reasonable plant-specific estimates of the biodegradable influence COD fractions, and to provide reasonable estimates of the critical missing operating data. And we needed to do this using only the routine plant monitoring data that we'd been provided. So the details of the development of this tool have been published in Water Science and Technology. It's open access, so you can download it for free. So if you're interested, you can go ahead and do that. But I'm just going to go over the basics. So our approach was to first of all specify initial set of fitting parameters which reflected the data that we needed to estimate, to develop a simplified mass and COD balanced steady state model of Kwamashu, and then determine which parameters were practically identifiable through a stepwise regression process, and finally transfer the optimized parameters to the infinite fractionator and West process model of Kwamashu. And the tool itself was implemented in R, which is a free statistical analysis software. So the tool consisted of three parts. The first was the simplified steady state model. So we sort of simplified the West layout into the model shown below. Consisted of a fractionated raw sewage, a primary settler which split the sewage between the anaerobic digester and activated sludge tank, and the output to the secondary effluent in the filter cake. There were no recycles, no nutrient removal calculations, though there was nutrient release in the anaerobic digester. The second part was the parameter estimation, by fitting the data to the simplified model. And the final step was a parameter selection process, or a parameter identifiability subroutine. And parameters were considered practically identifiable if changing them from their default values resulted in a significant change in how well the model fits the data. And practical identifiability is a function of both the data and the model structure. So basically this procedure would say, can we estimate the parameters using the simplified model and the data that we currently have available? I don't know why my presentation keeps running away. So this last step is why this was implemented in R and not in West. You can do parameter estimation in West, but you can't automate the parameter selection as we did here. Okay, right. So a lot of thought had to go into the initial fitting parameter selection, so they would answer the questions that we needed answered. So there were parameters for the influent fractionation, the missing internal flows, some component compositions, the relative removal efficiency of different components in this primary settler, and the representativeness of some of the data sets. And we had 12 sets of fitted measurements on the composition of the raw sewage, settled sewage, secondary effluent, some sludge streams, reactor concentrations, and the total sludge cake production. So in this analysis, 10 of the 13 parameters were identifiable. So that included the unbiodegradable fractions in the raw water, the flow split to the anaerobic digester, which allowed us to calculate the hydraulic retention time, the sludge wasting rate, which allowed us to calculate the sludge age. The 3 parameters that were not identifiable were F-CODIF, which is the fraction of the influent COD, which is soluble or filtered, and then the non-settling fractions in the primary settler, which were represented as FN and ISS, which is a non-settling inorganic suspended solids, and the and FNS code up, which is the non-settling unbiodegradable particulate COD. So we didn't do a separate structural identifiability analysis, but if we dig into why these particular parameters were not identifiable, it actually had to do with the structure of the simplified model. And essentially, the model couldn't distinguish a unique fractionation of the settled sewage in terms of soluble versus biodegradable, soluble versus particulate biodegradable, and unbiodegradable inorganic versus organic, which explained the observed data. But these results do suggest some relatively simple solutions. So filtered COD and inorganic suspended solids of the raw and settled wastewater aren't necessarily routine, but they are pretty simple measurements. Any wastewater lab should be able to do them. So you could add some of those measurements to your routine measurements when you want to do modeling, and you're going to reduce the uncertainty in the fractionation significantly. The tricky one is the unbiodegradable particulate, which requires more advanced techniques to measure. However, if we look at the structure of the steady state model, we can see that this is the mass of the unbiodegradable influent particulates in the reactor is the product of the flux into the reactor, which is uncertain, and the sludge age, which is uncertain in this case as well. However, if you could have had a reliable data for the sludge age, in other words, we had the operating records, and we'd fixed the sludge age, then this fraction would in fact have been identifiable. So with at least with a decent data on the sludge age, even the unbiodegradable particulate COD and the settled sewage can be estimated. So once we have our optimized set of parameters, we can transfer it into the WEST models, and this shows the overall fit between the modeled and measured data, which was pretty reasonable compared considering what we had to work with. So in conclusion, the COD fractionation tool can estimate raw and settled sewage COD fractionation and other mass balance parameters from routine plant data. And it addresses a significant barrier to modeling in practice, making the benefits of modeling available to a wider range of municipalities. If you want to explore the KwaMashu model for yourself, you can, because it is it's actually a sample which is provided with official West release. You can access it from the Getting Started panel, and it's called the MDemo PWMSA whole plant. But there's a bit of a caveat. We discovered some issues with the latest release. So up to West 2024, it's fine. If you want to look at it in West 2025, please contact us for a repaired version. So just briefly, in the sample includes a set of charts showing the balance in different parts of the plant. Sorry, for the different parts, the different components that we're interested for in terms of resource recovery. Let's see if I can go through this without the animation going wrong. But for example, for the phosphorus balance, there wasn't a phosphorus removal plant. So most of the phosphorus is going out in the effluent. If you add phosphorus removal, it will be transferred to the waste sludge, which is thickened in the DAF, and ultimately to the sludge cake. Man, okay. There's a COD figure which shows the fate of the COD fractions in the plant. So, for example, the red rectangle is the okay. You know what? Okay, yeah, sorry. The red is the unbiodegradable soluble that goes straight into the effluent. The dark blue is the unbiodegradable particulates, which mainly end up in the raw sludge and eventually in the sludge cake. Oh, not showing that. The biodegradable particulate is gold, so some of it goes to the sludge, to the primary sludge, and is converted to methane. And the rest, along with the teal biodegradable soluble, is oxidized, and that's in the activated sludge reactor. So that's our aeration requirement. Oh well, whatever. And some of it comes biomass, which ends up in the waste sludge. The energy recovery is represented by the methane production. And if you add thermal hydrolysis to increase the biodegradability of the sludge, then let's see, the part you can increase, the increased potential comes from the unbiodegradables in the raw sludge and the DAF sludge, and you can potentially increase energy recovery. So that's it. I should just acknowledge this fund work was funded by the Dunedin Fellowship Center and eThekwini Water Sanitation. And we're almost out of time, but if there's any questions, I'd be happy to hear from you.
Super, well done, Barbara. You've managed to get that in 5 minutes left. You did start slightly late, so yeah, I think you've kept quite well to your time. Are there any questions from the floor? The question from my side, Barbara, is the integration with the R model. It looked like you're sort of doing a sort of iterative analysis there with the actual West coupled with that. How easy was that achieved? Did you do it through some sort of API setup, or is there some method of feeding the results, etc., between the different modeling applications?
No, at this point, not. It was manually transferred. So this would be a first step in the calibration of the West model, and then once you had your basic mass balance right, then you would continue and do the more normal calibration, which might involve kinetic parameters. So this is sort of a prototype, and it's not it's not currently integrated with West. I should also point out that the downside is that the plant model is specific to Kwamashu. We have adapted it for one other plant. It's not that difficult, but yeah, right now that part is certainly not automated. It's really a data pre-processing tool.
Oh, okay. Right. That's good. Are there any other questions? Yeah. Can you see the question in the chat there, Barbara?
Yes. So yes, it was only from the lab data because, as I said, all the sensor data had been lost. There should have been sensor data, but it wasn't available to us because of the load shedding, essentially. Yeah. So so there should have been more flow data and things that would have been helpful and were lacking, and that was part of the motivation for the development of the tool. Another thing is that at the time, the fractionator parameters couldn't be used in the West parameter estimation. The way it was set up, it just they weren't accessible to be used like that. Now they are. So that if you didn't have this issue of lack of internal flow data, I think we could have done it in West. Just if we only were concerned in fractionation of the influent, it could have been done in West. It was really the lack of the other data which made it necessary to develop a tool where we could, which had the parameter selection facility, because you have a whole lot of parameters and they sort of interrelated. And you put that into a West model, it's just going to um, it's probably not going to work very well.
I think you mentioned that this was a work in progress sort of model. So you anticipate that as these sensors come online, etc., that everything will be integrated into the modeling, and you'll be able to get more sort of solid results and more effective results from the West modeling.
Sure. Yes. Yes. Yeah, that's sort of up to Teguini at this point.
Okay. I see there's another question there. Does the sensitivity of the data matter in the model development? Because from previous presentations, it was clear that the frequency was not that good.
Yes, of course. The the thing is, you do the best with the data that you have. If it's not very good, then there's going to be a lot more uncertainty in your results. What the probabilistic fractionator and the COD fractionator tool do is they try and fit the overall mass balance. So so to get the different parts uh, to get the different parts of the model to agree with each other. Because let's say if you're only focusing on your secondary, your effluent quality, then you may be getting quite wrong predictions for your sludge production. So, and then this model sort of forces the fitting to take both into account. And that was part of the motivation. We started out just with the West model, trying to make it fit the data sort of by manual adjustment, and it was clear that there was something systematically wrong with with the data, and it wasn't possible to get the different things to agree. And so this is why this tool was developed, to look at everything from the raw to fractionation to where the different solids and COD components were going, and try to find a best fit solution to explain what was going on.
But thanks very much, Barbara, for that. I'm going to end the sessions now. I will stay on for 5 minutes, and I was just wondering if you would mind, the presenters just mind staying on for 5 minutes for any further questions. Otherwise, you're welcome to head out and leave. But I'll just leave the session open for a little bit longer. Barbara, I think I've got one last sort of question for you, because I think both you and Chris sort of focused on this with mainly because of lack of input information related to sort of operations and measurements in the South African scenario. I'm guessing the ultimate sort of requirement related to these types of things is to see how it can improve wastewater treatment works overall, and improve the sort of operations of those. Do you have any sort of, I guess, anecdotal, perhaps measured insights into whether these sort of interventions have improved the operations of the different plants that you've been working on?
So that's a bit of a sore point. It's we can suggest things, but the municipalities have to implement them, and that's been a sort of the let's say there hasn't been the progress that we hope to see in terms of implementing any of the recommendations. So we did a few years ago present to the municipality about using models for decision support. So this is it's not the technical side of modeling, it's the engaging decision makers part that seems to be lacking. So yeah, that's another whole topic.
No, I'm laughing because it's something that I mean, obviously we deal with in many respects, is that you get through to the end of the application of these models, and the reason that you're running them is to prevent you from having to actually physically experience some of the problems associated with it. And there's obviously cost savings, and those types of things can be generated from a lot of these applications. And yes, sometimes the recommendations aren't put in place, but yeah.
Yeah, I mean, what I can say is our colleagues at it's a greenie. They wanted to use the models for risk analysis, and the kind of risk is like, if this equipment breaks down, how bad is it going to be and how long do you have to fix it? That was the sort of things they were interested in. And they've built a number of these skeletal models. So there's quite a good modeling group at Etuguini. The problem is getting the management to pay attention.
Yeah.
Yes.
Nice.
I mean, so I think if you look at the situation in wastewater treatment plants all over the country, it's in the news how little attention is paid to the technical aspects. It's all they are managed by people, or at least at the level where people control the budgets. They're managed by people who aren't interested in the technical issues. Not at the level of engineering personnel. That's we had good relations with them, but we never ever got through to the people who manage the budgets.
Yeah.
Yeah. So yeah, there's a lot of potential there, and I think a lot of good work in laying a foundation. But yeah, we're still waiting for the municipalities to move it forward.
Fair enough. Yeah, I think that's a general thing, is how do you translate some of the technical information into or major budget speeches, kind of the thing, or financial applications. So yeah, maybe something that all us engineers and scientists should work on.
Yeah, indeed.
Yes, no, absolutely second that. And I think that is the big difference between what happens here and what happens overseas. I mean, there you find that the management is really interested in getting the solutions through.
Sometimes.
And they support the modeling.
Yeah, exactly. That's good. All right. Well, I think I'm going to leave it on that poignant note, I would say. And yeah, okay. I see that. I'm not even going to try to pronounce your name, but yes, go for it. And comment, please. Can I call you McKees? Okay. All right. Thanks, everybody. And thanks very much for a very
Sorry, can you hear
informative
me?
news. Yes, yeah. Sorry, go for
Can you
it.
hear
Yes.
me? Sorry. I wanted to ask two questions. Thanks for the presentations. They were quite informative. So the first part was, from everything that we've seen here, is that all the modeling, from what I think Enrico shared in the beginning, and the two presentation of the modeling, was based on mechanistic models, right? So understanding what really is happening within the plant and understanding, for example, the fractionation. Is there a role of more black box models in terms of getting a quick turnaround time to give answers to the municipalities, etc.? And then the last point, which, because I'm South African and I'm based in Leuven, and I'm quite interested in the South African context, and I'm a student, so I'm not currently in industry, but are we not showing any financial benefits towards these models, right? So in terms of saying this is what it will save you as the municipality, in terms of them getting a buy-in into what excites us as engineers or as scientists. Thank you.
Yeah, my sort of one comment associated with black box versus processed based modeling applications and stuff like that is I get a little bit nervous when you're applying sort of empirical black box approaches to resolving certain problems. There's no question that they're useful, but they don't necessarily understand the causal sort of links and processes related to these things from a physical breast application process, and that can be problematic because it can give you incorrect answers because you can't just sort of apply one sort of black box model to another scenario because they're kind of calibrated and set up for their specific scenarios in these setups. So I think in many cases, the more process-based applications with links to things like we saw with Barbara, we've got the R modeling running, can actually be more useful in those contexts. But yeah, I don't know whether there's much that you can do, but I think that there's a lot of these processes that can be set up that are already available and maybe can be applied much easier. But that's my sort of application, and I'm not a West sort of scientist. I'm more of a hydrologist and use these models in different sort of applications that DHI provides. So I don't know whether there's any comment from the West guys from that side of things.
Yes, I would comment. I've had a little vicarious experience of what's it, artificial intelligence type models. And the issue really is that they come into their own. They're very useful in data-rich situations where there's a lot of data to calibrate and where you can pick up patterns. Now, we in wastewater treatment are largely operating in a very data-poor situation. I mean, as we've seen, there's a lot of data, but it's really not enough to cover all the gaps. And so the type of mechanistic modeling that we are doing is trying to use physical principles to bridge those gaps in the data. And so, but I mean, there are obviously situations where you might have a data-rich situation. So if you've got a sensor in a stream and it's giving you measurements every minute or something, then that kind of situation can be dealt with an artificial intelligence, shall we call it, type of approach. So there's, and I think what is coming is hybrid models where part of the system, which is data rich, can be handled in that way, and the bits which are data poor need the mechanistic models to fill in. Now, what was the other thing? What was the other part of the question? I've forgotten.
That part was, are the municipalities not seeing a financial benefit to these models? Especially if you look at eThekwini and KwaMashu.
Yes, no, they definitely are not. And it's because they aren't interested, really. We can do it. And I would actually point out that our colleagues at UCT are really working hard in that area. We were, as you will have gathered, we were more interested in the getting the data right. That was really our focus. But the UCT people are working on the the costing of different scenarios and so on, and in the South African context particularly. So yeah.
Yeah. Okay. Christopher, do you want to clarify that point, or was that something that you were asking Ms. Swane Corsi to just elaborate on?
Yeah. Can you hear me?
Yes, yeah. Okay.
Yeah, it was just a small comment around black box. I think with the advancements that have been made, especially with data-driven modeling, I think black box is almost too generic these days. You've got, tree-based models. You've got these large neural networks with deep learning. So I think, as Chris Brook had mentioned, there's a lot of caveats or pre-definition needed when you need lots of data. For instance, as you said, data-rich environments. But one thing that we've been working on a lot in our digital twin is trying to make predictions without data-rich environments. So when you train the model, you need to understand that it won't be able to predict outside of those boundaries. So data-driven models are terrible at going outside of ranges that they've seen before. But in terms of getting something up and running quite quickly, we find the training times to be extremely efficient. You can have a model trained and making predictions within 10, 15 minutes if the data is in the right format. So to answer the question on value, I think there's value in data-driven modeling for sure, but there's also a lot of room for error, because without the knowledge of the mechanical and mechanistic biology or bioprocesses behind the scenes, you can just take the data, assume that it's correct, and start making wrong assumptions or wrong predictions. So as Chris Brook had mentioned, with hybrid modeling, we're doing that a lot more and more in our projects for N2O emissions, for instance. That's a big application that we see with this nitrous oxide, is that the model's just slightly lacking with the accuracy that we need. So we're trying to now research and develop methods where we train data-driven models to correct the mechanistic models in terms of the predictions that they make for end-to emissions. So it's kind of like a leapfrogging back and forth between the two domains. And that I think has a lot of value instead of just relying solely on one application or the other.
Excellent. Thanks, Christoph. Yeah. Another UCT graduate, I believe. Another South African. Yeah, so that's fantastic. I'm going to end off on that sort of note. I think just to comment, I think that there's, while in some of the South African scenarios, I think that the cost benefits are not necessarily that pronounced. I do think that there are many cases overseas where DHI have done stuff that do definitely show specific cost benefits and in the applications of these modelings and the application of the twin plants. And yeah, I'd like to thank everybody for joining, and we're going to close the session. Thank you very much. And thanks again to the presenters, and we will make everything available to you as soon as possible. Okay. And Cornelia's pretty efficient, so I'm sure it'll be happening in the next couple of days. Thank you, everybody. Bye-bye. Enjoy.
Bye.
Bye.
Bye, everyone.